All right, chemistry. We're now on to the second and last unit of Unit 3 on gases, and this is just called Basic Gas Laws 2, just some more facts about gas laws. So here we have a problem. It's very similar to the ones we've been doing in class. How many grams of water, H2O, will be produced from the combustion of 12.4 liters of CH4 at STP? That is at 0 degrees centigrade and 1 atmosphere pressure. Standard temperature pressure. Okay, so let's go ahead here. And we're starting with 12.4 liters of CH4. So if you look at this, we have three levels. We have, first of all, we have our chemical equation. And the chemical equation speaks in the language of moles, of numbers of particles. So if we want to do anything between these different compounds, we have to be in moles. So from the top, we can convert liters of gas into moles by using the relationship 1 mole equals 22.4 liters. And you notice that's true for all four of the compounds there, all four of the gases. It's 1 mole equals 22.4 liters all the way across. Down at the bottom is the relationship we've used before. We were using long ago, about a month ago. And that is we can convert from grams into moles using the molar mass. You have to compute the molar mass of each compound there, and using that relationship that 1 mole equals some number of grams of that compound, you can convert from grams to moles and from moles back to grams. So we're going to go ahead and do this. So we're starting with 12.4 liters of CH4. And it's asking us how many grams of H2O. So that means our question mark is going to go down there in the bottom right. It's way down at the bottom in the grams row and way over on the right underneath H2O. So we need to find a path to get us from the 12.4 liters to the question mark. So what we're going to do is come down and down. And we use the 1 mole equals 22.4 liters to convert the 12.4 liters into some number of moles. Then we come across, and that's the only place we can go sideways is inside the chemical equation. So we have an equivalence there of 1 mole of CH4 equals 2 moles of H2O. We don't care about O2 and CO2 in this problem. We're just skipping past them. So 1 mole of CH4 equals 2 moles of H2O. That'll put us over in the moles of H2O box. And then our third conversion is to come out using the molar mass of water. That's 1 mole equals 18.02 grams. And that will get us to grams of water, which is what we want for our final answer. So you can see that this is 3 conversions. So we write our equation up on the top. We start way over on the left, 12.4 liters CH4. And way over on the right is what we're trying to get to, grams of H2O. And we see it's 3 conversions. So we're going to have 3 boxes there. So now our first equivalency is 1 mole equals 22.4 liters. So you put 1 mole over 22.4 liters or 22.4 liters over 1 mole. So which of those two are you going to put in that first box? Well, the answer is the first one, because you have liters of CH4 in the 12.4 liters of CH4, so you need liters of CH4 on the bottom of the first box. So now liters of CH4 is going to cancel with liters of CH4. And if you did the math at this point, and we don't do this, we never did in class, we don't normally do that, you could see down in the box down below, we have 0.554 moles of CH4. We really don't care about that number. That's just an intermediate calculation just to demonstrate what that number would be there. But we don't compute that number. Okay, now we're ready to move on to the second box. And that is 1 mole of CH4 equals 2 moles of H2O. So that means we can write 1 mole of CH4 over 2 moles of H2O, or 2 moles of H2O over 1 mole of CH4. So think about it. Which of those two are you going to put in that second box? Well, in the first conversion up on the top, you have moles of CH4. So that means we have to have moles of CH4 down in the bottom of this second box. So we're going to choose the second one. We're going to put that in. And moles of CH4 cancels with moles of CH4. So now, if we did the calculation with these two conversions and the 12.4 and these two conversions, we would end up with 1.1 moles of H2O there in that red box right underneath H2O in the equation. But we're not interested in that number. We're only interested in our final number where the question mark is. So now we have one more conversion. It's 1 mole of H2O equals 18.02 grams of H2O. So the two conversion factors are 1 mole of H2O over 18.02 grams of H2O, or 18.02 grams of H2O over 1 mole of H2O. So which one of those is going to go in the box up above? Well, you have moles of H2O in the second conversion, so you need that to cancel out. So we're going to put the second one there. There it goes. So moles of H2O cancels with moles of H2O. And now the last man standing, the only thing that didn't get canceled out is grams of H2O, and that's what we have in our final answer, so we know that we've set the problem up correctly. So now it's just math. You multiply everything on top. 12.4 times 1 times 2 times 18.02, and then you divide by everything on the bottom. Divided by 22.4, divided by 1, divided by 1. And when you do all of that, you get 20.0 grams of H2O. And if you want, you can write it in the box down at the bottom there. You don't have to do that. 20.0 grams of H2O is our final answer. Okay, we can move further into this course. As we move further into this course, unit of measurement cancellation will become more complicated. So use the principles of fraction division to cancel units. So if two levels of the fraction have a common word, then the units on those levels can be canceled. So let's say we have a fraction on top of a fraction. So we basically have 4 levels there. Numerator top, numerator bottom. That's the fraction that's in the numerator. And then you have a fraction down on the bottom in the denominator, and we'll call that fraction denominator top, denominator bottom. So if the units of measure, if you have 2 of the same units of measure, and they're in one of those levels that has a word in common, then they can be canceled. So let's just take an example. Let's say we had liters up on numerator top. If we also had liters down on numerator bottom, they could cancel. The liters could cancel with liters because both of those levels have the word numerator in common. Now let's start again. What if you have liters up in numerator top and you also have liters in denominator top? Then those liters could cancel because both of those levels have the word top in common. So you could cancel liters in numerator top with liters in denominator top. Okay, start again. Third example. Let's say you have liters in numerator top and liters down at the very bottom in denominator bottom. Those liters could not cancel because the words numerator top and the words denominator bottom don't have any words in common. So you can't cancel the very top and the very bottom, liters in the very top and liters in the very bottom. And it works the same way with the other levels. If they have a word in common in their name, then you can cancel them. Okay, so here's an example. And it looks a little complicated. You won't get any real world units of measure cancellations that are this complicated, but it's just a little puzzle. Just treat it like a little puzzle. So what can we cancel here? Well, we can start with kelvins. That's measures of temperature. You have Kelvin in numerator top and Kelvin in numerator bottom. They both have the word numerator in common, so they can cancel. Okay, try to find 2 others that'll cancel. Well, how about atmospheres, ATM? You have atmospheres in numerator top and you have atmospheres in denominator top. They both have the word top in common, so they can cancel. How about liters and liters? Again, numerator top, denominator top, they both have the word top in common, so they can cancel. How about grams down there at the bottom? You have grams in denominator top and grams in denominator bottom. They both have the word denominator in common, so they can cancel. Moles and moles. You have moles in numerator bottom and moles in denominator bottom. They both have the word bottom in common, so they can cancel. So the only things that we've not canceled yet are the grams in numerator bottom and the liters in denominator bottom. Now you have to remember the principles of fraction division. That fraction on the bottom, what you can do is flip it and then multiply. So you take the top fraction, you leave it alone, and it has 1 over g. You can see that. There's nothing on the numerator top, so that's basically a 1 up there. 1 over g. And then in the denominator, you have 1 over L. So what that 1 over L does, you flip it and multiply it by the top. So that L flips all the way up to the top, like that, and your final units of measure is L over G. Again, it's just like fraction division. You flip the bottom and multiply. That's what we just did. We took 1 over L, we flipped it so it becomes L over 1, and the L goes all the way up to the top and multiply, so you have liters over grams, okay? So it's a little tricky, but with practice it's not so bad. Okay, gas density. Gas density is the mass of the gas divided by the volume it occupies. So density equals mass divided by volume. So here we have a gas molecule in a certain amount of volume there, that yellow box. There's one hydrogen gas molecule in the volume to the right. So when a second molecule is added, then the density doubles. You have twice as much mass in that same volume, so you've doubled the mass, therefore the density has doubled. Density can also be increased when the volume is decreased. We'll show that on the next slide. So sometimes density uses the Greek letter rho. It looks like a scripted P. It's called rho, but we're going to use D because it makes more sense for density. So gas density is the mass of the gas divided by the volume it occupies. So there's the same formula. So the density could also be doubled by reducing the volume. So in this case, we just kept one hydrogen molecule, but we cut the volume in half. That also doubles the density because you have decreased the volume. You kept the mass the same, but you've decreased the volume, so that means the density has gone up. Temperature is the average kinetic energy of the gas particles. Kinetic energy is given by the formula Ke, kinetic energy, equals 1/2 mass times velocity squared. So m is the mass and v is the velocity. You can think of it as speed. By increasing the temperature, we increase the average kinetic energy of the particles. Okay, that's the definition of temperature. It's the average kinetic energy. So if you increase the temperature, you've increased the average kinetic energy of the particles. Since the mass of the particle remains constant, in other words, it doesn't get any heavier or lighter just because you increase the temperature, then increasing the kinetic energy increases the velocity of the particle. So look back at that formula. If you've taken physics, you've probably seen that formula before. If Ke in that formula up above goes up, then on the right side of the equation, mass can't go up. It's got to stay the same. Therefore, the only thing that can go up along with kinetic energy is the velocity. So that means as kinetic energy goes up, the velocity goes up. That means the molecule gets faster. So let's follow the reasoning again. Temperature increases kinetic energy increases velocity. Therefore, an increase in temperature is going to increase the velocity or speed of the molecule. So the way to think of temperature is increasing temperature increases the speed of the molecules. That's the thing to remember. So let's say we have particles of two different masses in a container at the same temperature. That means they're going to have the same kinetic energy. So assume the following. Mass of particle A is 2 atomic mass units. Mass of particle B is 8 atomic mass units. And let's say they're both at the same temperature, so they both have the same kinetic energy of 16 joules. So the formula for kinetic energy is what we saw on the previous slide right there, 1/2 mv squared. So both particles have the same kinetic energy, 16 joules, so we can compute the velocity of each particle. So for the lighter particle, particle A, you take the formula 16 equals Ke, 1/2, mass is 2, velocity squared. Don't worry, you won't have to solve this in class or on an assignment or a test. It's just a demonstration. But if you do the algebra on that, you'll find out that the velocity of particle A, that's VA, is 4 whatever, meters per, we can say meters per second. Now let's do the same thing to the heavier particle, the 8 AMU particle B. So again, the kinetic energy is 16 because the temperature is the same. That equals 1/2 the mass, which is 8, times VB, the velocity of particle B, squared. So when you solve for the velocity of B in that equation, you get the velocity of B equals 2. So particle B was 4 times heavier than particle A, and it moved half as fast as particle A. And that would make sense, that a heavier particle is going to move. If you put the same amount of energy into a heavier particle, it's not going to move as fast as the same amount of energy into a lighter particle. Now, from this relationship, a law of chemistry was derived, so we'll see that here. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. This leads to the following relationship for 2 gas particles called Graham's Law of Effusion, and we'll define effusion later. And it's simply this. The speed of the lighter particle compared to the heavier particle is simply this. You take the fraction of the mass of the heavier particle over the lighter particle, and then you get that number, and then you take the square root of it, and that will tell you, it doesn't tell you an exact speed in meters per second or miles per hour, but it tells you how many times faster the lighter particle is moving than the heavier particle. So how many times faster particle A is than particle B in our last example? Well, the heavier particle was B, so you put that on top, that's 8. The lighter particle was A, you put that on the bottom. 8 divided by 2 is 4, and the square root of 4 is 2. And that's what we came up with for the how much faster A was moving than B on the previous slide. 2 times faster. So that's what Graham's Law of Effusion does. The relationship of Boyle's Law, Gay-Lussac's Law, and Charles' Law are as follows. So standard temperature pressure, we've mentioned it in class, and here's the definition again. Standard temperature and pressure, STP, is a temperature of 0 degrees centigrade, that's the freezing point of water, or in Kelvin that's 273, and 1 atmosphere. That's the normal atmospheric pressure at sea level where you live. Using STP and the ideal gas law, we can determine the relationship between the number of moles and the volume of a gas. We can determine that 1 mole of a gas, of any gas, is equal to 22.4 liters. So we've been using that relationship in our gas stoichiometry problems, so let's prove it using PV equals nRT. So there's PV equals nRT. So now we're going to solve it for volume. So what you do is you divide both sides by P, and you end up with V equals nRT over P. Now we're going to plug in our numbers. So we're interested in the volume of 1 mole. So N equals 1 mole. R is the gas constant, and T is the temperature at 0 degrees centigrade or 273 Kelvin. So we put that in for the temperature. That's standard temperature. Then standard pressure is 1 atmosphere, so we put that down on the bottom. Now we get to practice our unit cancellation skills. So first we cancel Kelvin with Kelvin. You have Kelvin in the numerator top, that's the 273, and Kelvin in the numerator bottom, that's the liter atmospheres over mole Kelvin, that's the one there. So Kelvin over Kelvin cancels. Now we have moles over moles, that's the mole in 1 mole, over the moles in liter atmosphere moles Kelvin, so that's numerator top, numerator bottom, so those cancel. Now we have atmospheres that'll cancel. You have atmospheres way up on the top, that's in numerator top, and then down underneath it's in denominator top. If you only see one level, it's the denominator. It's the top, excuse me, or it's the top. So it's numerator top, denominator top. So those two cancel because they have the word top in common. So now the only thing standing, the only unit is liters, and that's what we want. So now if you multiply everything on the top, 1 times 0.0821 times 273, divide by everything on the bottom, 1, you get 22.4 liters. So at standard temperature pressure, 1 mole of any gas has a volume of 22.4 liters. This means that 1 mole of any gas will equal 22.4 liters in volume. That's at STP, at standard temperature pressure. Dalton's law of partial pressure states that the pressure of a mixture of different gases in a container is the sum of the individual pressures of the gases. So the pressure, total pressure in a container is the sum of the pressure of gas number 1 plus the pressure of gas number 2 plus the pressure of gas number 3. So let's say the gas number 1 was oxygen and it had a pressure of 1 atmosphere, and gas number 2 was nitrogen and it had a pressure of 2 atmospheres. Now, why would it have a different pressure than the first one if they're in the same container? Because maybe you have 2 moles of nitrogen and only 1 mole of oxygen, so that the nitrogen would have a greater pressure. And then the pressure gas 3 is hydrogen, and maybe you have 3 moles of that. So you have 1 mole plus 2 moles plus 3 moles, or excuse me, 1 atmosphere plus 2 atmospheres plus 3 atmospheres would equal 6 atmospheres of total pressure in the container. So you just add up the pressures of the individual gases, and that'll give you the total pressure in the container. If the gases occupy the same container at the same temperature, then the pressure is directly related to the number of moles, what I just said. If you have twice as much nitrogen than oxygen, it's going to have twice as much pressure. So you can just say that the pressure of gas number 1, let's say that was oxygen, is N1 times RT over V. Well, the R and the T and the V are going to be the same if they're in the same container. So the only thing that's different is the number of moles and the pressure. For gas 2, the only thing different is the number of moles and the pressure. The R, the temperature, and the volume are going to be the same if they're in the same container. And same for pressure of 3. The only thing different is going to be the number of moles of 3, which we said was hydrogen. So the R, T, and V will be the same. So the ratio of the moles of a specific gas in a container divided by the total moles of the gas is called the mole fraction. So mole fraction is designated by that funny looking X. It's the Greek letter chi, and that represents mole fraction. So it's simply the number of moles of one of the gases over the total number of moles of gases in the container. Since the partial pressure of a gas P1 is proportional to the mole fraction, then if we knew the total pressure of the gas and we wanted to know what fraction of that pressure that we could attribute to oxygen, then we would take, let's just say we have oxygen and nitrogen in the container. Then we could take the moles of oxygen, put it up on the top, and then add the moles of oxygen and nitrogen together. That's the total number of moles in the container. That would give you a fraction that's a fraction of that that's oxygen. And you multiply that by the total pressure, and P1 would be the pressure of the oxygen. So let's see an actual example here on the next slide. So example, a container holds 2 moles of O2 gas and 1 mole of H2 gas. What is the partial pressure of O2 gas if the total gas pressure is 960 torr? So find the mole fraction of oxygen and multiplied by the total pressure. So there's the formula again. So 960 torr is the total pressure. 2 moles are oxygen. Down in the bottom is the total moles of everything. 2 moles of oxygen plus 1 mole of hydrogen. So that's 2 plus 1 is 3. So the fraction is 2/3, 2 over 3. So if you multiply 960 by 2/3, 2 over 3, you get 640 torr. So of that 960 torr, 640 of the torr is from the oxygen, and if you took the difference, that would mean 320 of the torr would be from the hydrogen. That would just be 960 minus 640 would give you 320 for the hydrogen. Okay, kinetic molecular theory is just a basic theory of how atoms and molecules in gas form react. So gases consist of here's the first principle, gases consist of large numbers of particles that are in continuous random motion. The combined volume of all the gas particles is very small compared to the volume of the container. That means the gas particles aren't right next to each other. They're spaced out pretty far from each other. The attractive and repulsive forces between gas particles do not exist. So when 2 molecules come close together, they can attract each other. But in gases, we assume that they don't attract each other. They're like little rubber balls flying around. One rubber ball is not attracted to the other rubber ball. They might bounce off each other occasionally, not very often, but occasionally, but they're not going to be attracted. They're not going to stick together. So this is the main characteristic of a gas. Gas particles are separate from one another. 4. Energy can be transferred between gas particles but does not increase or decrease. So when one gas particle bumps into another, it can transfer energy. It's like a bigger particle bumping into a smaller one can make the smaller one go faster and the bigger one go a little bit slower, but you don't decrease the total energy of the gas particles. And 5, the average kinetic energy of gas particles is proportional to the absolute temperature. So again, temperature represents the average kinetic energy, the average motion energy of the gas particles. This means that the temperature in Kelvin reflects the average kinetic energy. So that's called kinetic molecular theory. Okay, density and molar mass. There's a formula that relates the density of a gas with the molar mass of the gas. The molar mass of an unknown gas can be computed by the formula molar mass equals density times gas constant times temperature in Kelvin over pressure in atmosphere. The density, by the way, is in grams per liter. So where density, D is density, R is the gas constant that we've used before, T is temperature in Kelvin, and P is pressure in atmospheres. So example, what is the molar mass and possible identity of the gas with the density of 1.71 grams per liter at a temperature of 290 Kelvin and a pressure of 1.02 atmospheres? So we simply plug in numbers, and when you plug in the numbers there, so you have density on the top, R on the top, temperature on the top, and then down on the bottom is pressure, and you run the numbers on that, you get 39.9 grams per mole. Okay, now that doesn't absolutely identify the gas, but argon gas has a molar mass of about 39.9, so we might guess that it might be argon gas. Not guaranteed, but might be. Okay. Okay, the average speed of some common gas molecules ranges between about 300 and 3,000 meters per second at 25 degrees centigrade, which is about room temperature. Okay. So air consists of nitrogen and oxygen molecules which have about the same mass. Nitrogen is about 28 grams per mole and oxygen is about 32. So they're pretty close to each other. The graph to the right shows the fraction of common gas molecules at various speeds. So what you see there is hydrogen is the lightest of the gases, and so it's the fastest. So you can see more of its molecules are to the right on that graph. To the right is the higher speeds. So the lightest one is the fastest. That would make sense at a given temperature. The next lightest one, helium, is the second fastest. That's the green line. So it's to the right. Okay, then we get to H2O. H2O has a molar mass of 18 grams per mole, so it's kind of fast. Nitrogen's a little bit slower, it's 28 grams per mole, and oxygen is a little bit slower than nitrogen, it's 32 grams per mole. So basically, the fraction of the molecules is what's under those curves, okay? So the further to the right, the faster. Diffusion is the random movement of gas particles in an open space. Effusion is the movement of particles through a small hole. So if you open a bottle of perfume, and 10 minutes in a warm room particularly, and 10 minutes later you can smell it throughout the room, that's diffusion. It's the movement of molecules in an open space. Effusion is a specific experimental technique to understand how fast different particles move. So what you have is a container. So you see the one on the left, that's just diffusion. That's just moving around in an open space. The one on the right measures effusion, and what it has a small hole in it. And you put all the gas molecules on one side, and then you see how quickly do they start moving over to the other side. So if you put them all on the left side of the effusion container, and then you can measure how long does it take, how quickly do they move over to the right side. So that's called effusion. So that's an experimental process to determine the speed of gas molecules. Effusion is a laboratory process that allows the speed of gas particles to be measured because it focuses them into a known space. Mean free path is the average distance a gas particle travels before colliding with another gas particle. So the higher the pressure, usually the shorter the mean free path. Ideal gas behavior does not perfectly exist in the real world. Think of an ideal gas as this. It's a single molecule of some gas in outer space. There's no other gases around or molecules to bump into it, to interfere with it, to slow it down. So it's basically a molecule that can move freely. If ideal gas particles are not interfered with, they move freely. Gases behave most like ideal gases when the temperature is high. This is because the particles have enough kinetic energy to avoid being attracted to other particles. If the particles slow down enough and lose enough energy, then they start sticking together. Then they don't act as a gas. And if they do that enough, they start to act like a liquid. they start to stick together like a liquid would. But if you can keep the temperature high, they're going to move around at fast enough speeds that they won't stick to each other. So that's one thing that will help cause a gas to behave more like an ideal gas, if the temperature's high. The other thing is if the pressure is low. This is because the particles are spaced far enough apart to avoid contacting each other. So high temperature and low pressure make the gas act most like an ideal gas. If you have the opposite, low temperature and high pressure, the molecules will tend to want to stick together and bump into each other more, and they will not behave like an ideal gas. And that takes care of this, our final lesson in gas laws. We're going to move on to a new unit soon. So go ahead and finish these assignments, and we will see you on the next lesson.